let's get physical now. And after seeing the four vectors and all transformations and all these sort of things, we're now going to look at relativistic mechanics. And with this, we are going to look at the behaviors of particles. In the space-time, if you want. Good. So, first thing to know is where your particle is. And you know where your particle is. We get our x mu is going to be equal to x0, x1, x2, and x3. That's the core position of your particle. Your particle is here, or your particle is there. And this is not invariant. Right? If we change the coordinates, the components are going to change. This is not invariant. Then we have the word line, which is the trajectory that is covered by our particle, that we can express in terms of an affine parameter, and usually people use tau. So where is your particle in a certain location of the space-time when an observer located sitting on the particle, if you wish the time measured by the particle, is a certain tau. Word line. Okay? So it's going to be a trajectory, which, as I said, have some constraint. Particles cannot move however they want, they're pleased in the space-time. Because again, we have x, ct, we have the diagonal, where photons are living. And for photons can only be here, 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 and here. They cannot be here. They cannot be here. Okay? They move along, they are null. Their position is described along the word line would be this straight line. If we have a massive particle cannot move faster with respect to the speed of light, and then the trajectory can be of this sort. Okay? Here it's not moving, then I'm moving right, and so on. But it cannot be of this sort. Because in this location, the particle would be sitting in its own light cone, something like that. And if the inclination of the trajectory is smaller in its CT diagram with respect to the diagonal, it would mean that this particle is faster than light. And it cannot be. Okay? Therefore, at each location, the particle is carrying its own light cone, and it must stick to the rule of I am a massive particle, I can move only in this direction, forward in time, not back in time. So you cannot have a particle that is doing something like that, going in this direction. This is not allowed. And these are the so-called word lines. Okay? Then we can start to add new ingredients, which the first one of which is the four velocity. As we have four vectors, four positions, we can define four velocities, which we define with a vector that now I call u. It's a four vector, and is defined as the x mu over the tau. If you wish, is the velocity with which a particle is seeing the frame passing under its feet in intervals of proper time tau. And if we now link it to the frame, not of the particle, but of somebody else, then would be the x mu over the t multiplied by gamma. So here what I did was just to use the expression of the proper time that we have seen in one of the very first lectures. Okay, so I just express the tau is the t over gamma. And if I want to look at all components, u mu is equal to gamma, if it multiplied by gamma, c dt over dt, this will be the dx0, right? C dt is dx0. And then we have the x1 over dt, the x2 over dt, the x3 over dt. And now to be a little bit lighter in writing, the t and the t goes away. So we have gamma c. And then we have the velocity, the three-dimensional velocity. You see, we have the x1 over the t, the x2 over the t, the x3 over the t. And we can write it like that. Okay? If I want to group as well, I can write it like that. Okay, now take care about the meaning of this bar, because this is a vector in the 3D components of space. Okay, it's not a full vector. I don't go over, I will go fast over that because the meaning should be clear, right? We are living in a 4-dimensional space, time axis, 3-dimensional axis for position, okay? So for velocity. Good. And this guy, again, is not invariant. Not invariant. Because it's a 4-vector, and the components of a vector transforms under Lorentz transformations, and they're not always the same. But if we look at the norm of this vector, therefore we are getting our vector u. Now you see I'm still using the bar, but this is 4-dimensional. This was 3-dimensional, only space. Okay? Several people don't even write the bar. You should just keep in mind that these are vectors. Okay? Just to remind you that these are vectors, I put the bar, but remember that here is 4D, there is 3D. Okay? You should be clear on how they appear where. Okay. And then what? This is equal to u mu, which is equal to mu u mu. And now what? We can express our component of the velocities as we express it here, right? Therefore, let me go quickly. Let me continue here. So we continue with the velocity. And we get c squared gamma squared. C squared gamma squared. And then this is, we have this scalar product, we have the multiplication. I need to sum up the squares of the components. So by summing up, remember that there is the metric with the minus in front, therefore we have a minus 1 plus beta modulus squared. So that's equal to what? This is equal to minus gamma squared. Minus 2. Okay. Good. Which is equal to minus c squared. For u mu is equal to minus c squared. And this is invariant. and is always equal to minus c squared. Always. Okay? That's because this gamma and gamma disappears. They cancel each other. Then, similarly, we can define the Theor acceleration. And guess what it is? Well, let's call it A as acceleration. Mu, it's a Theor vector. The u mu over the tau is the derivative of the Theor velocity. And the components, A mu are equal to what? The over the tau, that's what the derivative is, of u mu. Therefore, we are going to have gamma c velocity. That's the derivative of all of that. Derivative is a ring operator. It's going to be applied to each component of the vector. What I can do as well is to change this gamma and express it in terms of time through gamma. Therefore, we are going to have gamma over the t of gamma t v. And now we just apply the derivative to this product of functions. Well, actually, gamma c is going to be constant. So we have gamma, and we have gamma dot c plus gamma dot v plus gamma v dot. Okay? Here you see we have gamma c, so it is just a function multiplied by a scalar. Therefore, we just have the scalar and the derivative of it. Whereas here we have a function times a function, therefore we need to apply the product rule of derivatives. Therefore, the derivative of gamma times the function untouched plus the other function untouched times the derivative of the other function v. Okay, just product rule. So you see that when we're dealing with Theor accelerations, the things get a little bit more complicated than what you would expect or than what you would have in standard Cartesian space, okay, Euclidean space. Okay? Plus, where? Ah, yeah. Right. Of course, thanks. Because we made the multiplication for the first component, this one, and then the multiplication, sorry, the derivative of the first component, and then we have the derivative of the second component. Okay, good. Well, now we can look at something, some property of this Theor acceleration. Because again, you see there are few weirdnesses here, but there are even more weirdnesses. Because we can note, now I do it this way because it's just faster. I can just investigate what is the variation of the of u mu. Okay? I can just give a look at that. You could say, why would you do that? Well, you will see in a moment. Okay? So, what do we have? The derivative with respect to the proper time of this product of functions. Therefore, we need to apply the product rule. Therefore, we are going to have the u mu over the tau times u mu plus the u, plus u mu, the u mu over the tau. Product rule. And this is equal to what? This is equal to twice this quantity, because we can lower this index and we can write this index. This is the very same scalar product, right? Index up and down is the same. We have seen this in the past lecture. Okay? It's anyway a repeated index where you have the summation or subtraction, depends on the, again, keep in mind that there is the metric hidden here. And if I express it this way or that way, it doesn't change. Plus, we have seen it with the properties of one forms, that we can have one form swallowing a vector, giving a scalar, or a vector swallowing a one form. Therefore, we can flip the two as we want. This is always the very same scalar product. Okay? One can write it like this, or can write it like that. Doesn't matter. Good. I'm stressing that because it's important for the computations. Therefore, if I do that, you see that we have twice this amount. Let me use the same mu to reload it, and the mu. Okay, up to here, who cares, right? What's important? Well, let's remind ourselves that this guy is equal to minus c squared. It's an invariant. It's a constant. What's the derivative of a constant? 0. Therefore, this is equal to 0. What do we learn by making this little thing? That this guy, the x mu over the tau, which is our 4 acceleration, is always orthogonal to a mu. They are always orthogonal. In a 4-dimensional sense. Okay? So you need to think that they're orthogonal with respect one with each other in a Cartesian way, but through the metric, which is hidden here. Okay? So if you make the scalar product of A times mu, they are always equal to 0. Okay? In 4D. It doesn't mean that the acceleration in 3D is orthogonal to the acceleration in 4D, the special components. Okay? And keep in mind that, because this is useful. Plus, I want to do this little step because there are, these little tricks that are then very useful when you're going to solve the exercises, and you will need that at the exam, during the exam. Okay? Good. Now we can continue. And now that we have a 4 velocity, we could define, for instance, the 4 momentum. Here we are starting to touch the physics of particles. And what's this guy? Well, it's very simple. P mu, it's a 4 vector. And again, is defined in the very same way as we define the 4 velocities or the 4 acceleration. Let me stress the fact that this is a definition, okay? It's coming from nowhere. We just call the mu over the tau the 4 acceleration, okay? Good. Same we are going to do with our particles. I'm going to assume the particle to have a mass. It's a massive particle. A label with 0 because it's the mass at rest times u mu. And we will see what I mean with that. Okay? As we would do in the standard 3D momentum, right? Mass times velocity, that's our momentum. This is different, it's a 4 momentum and comprehend also a time component which is referring to the, a component which is referring to the time direction, okay? If we then use the definition of our 4 velocity, we just plug it into here, what we get, talking about components, so let's be precise and I put the parentheses as well. I'm going to have gamma, then we have M0 C, and then we have M0 E. So you see that we have two parts here. I call it 2, the first one, and 1, the first one. And I did it this way because the component 1 is explained right away, because we have the three-dimensional component. Remember that this is 3D. We have the three-dimensional component of the vector, 3D, okay? Only the space component are equal to gamma M0 V. And the interpretation is direct. If we are going to the non-relativistic regime, the transformation gamma becomes 1, but we get the momentum, the standard momentum, M0. Okay? Okay, the link to physics, the Galilean one, is straightforward. And we see by that it works. We can recover what we already know for non-relativistic particles. That's nice. Then we can continue with the other information we have, and it's a little bit less straightforward to understand. We have gamma, a mass, gamma is dimensionless, and then a velocity. Okay, what is it? I don't know. It's not that clear. Let's try to make it more clear, and let's explode our gamma. Let's write it in an explicit form. So we have M0C, 1 minus beta squared to the minus 1/2. That's just the definition of gamma. Then again, it's not that clear, so let's make a Taylor expansion. Let's make an expansion of this square at first order and see what we get. So we just get M0C, is the constant that I'm not going to touch. And then we have 1, the Taylor expansion, we have a minus here and a minus here, therefore we get a plus 1/2 beta squared. Plus, I would have the other terms. Okay, so I'm stopping at first order. Now, let's be tedious, and let's just multiply M0C times those factors. M0C, that's the first one, plus 1/2 M0C beta modulus square. And now I forget about the other terms, okay? I just forget about those. Then I'm super tedious, and I just collect 1/C. And what we get? M0, sorry, I'm collecting MC, so M0C squared, plus 1/2 M0 C squared. I will get, I'm not collecting C squared, C, therefore here I will get a C squared, but remember that beta is velocity over C. So beta is equal to velocity squared over C squared. And they are going to cancel each other. Remember C, I have a C squared, B squared over C squared, the C goes away. Now things are more clear. What do we see? This guy is the kinetic energy. Is an energy. Then this guy must be an energy. They're coming from the same object, must have the same units. Therefore, this guy is an energy. That's the energy of our particle at rest. Okay? That's the energy of our particle. And now you see where this mc squared comes from. Okay? This famous mc squared. Therefore, the component 2 is actually equal to E over C. It is this over C. Okay? The end, C of P mu is going to be equal to gamma E0 over C, P, and then we have the standard momentum. And this is our energy momentum. This is a key point because now we don't speak anymore about energy and momentum conservation as two different entities, but we are speaking about energy, momentum, conservation. And again, energy, momentum is a 4 vector. So the components transform one with each other, but the transformation is such that the modulus is an invariant as all 4 vectors. Okay? To give a look at that, let's try to look at the momentum, sorry, P and P. Again, stress the fact that this is a 4 dimension, so that we're going to look at the norm of this vector. I just compute the, given these components, I have my minus in front, and we have the energy squared over C squared plus theta squared. Sorry. So the 3D component, this is 3D. Okay? Just the norm of this vector here. And then I can also write it in another way. So we have P, and I write it as P mu. And if I'm using the definition that I gave up there, if it is gamma M0B, then what we get is M0 square U mu. That's definition of the for momentum as it's given up there on top. U0, U mu. Okay? That we get the M0 squared, and then we get U mu and U mu. But again, what's that? U mu, U. It's equal to minus C squared. Therefore, all of that is equal to minus 0 squared C squared. And this shows you that this guy is an invariant. Let me finish. Good. Let me use this little part of board. Now that we have these two expressions, you see they are the same, because this is just the scalar product. Therefore, this guy must be equal to that. And if we get the two expressions that are in the bottom board, we just have minus e squared over c squared plus b bar squared equal to minus m squared c squared. And I can just isolate the energy of our particle. E equal squared is equal to m0 squared c to the power 4 plus c squared and then e. So we have two components for the energy of our particle. One is the energy of our particle at rest, and one is the kinetic energy of the particle. Okay, and you see that they are belonging to the same energy. Yes. Good. So, little recap. Now that I have to wipe up before wiping up the board. We are done with the definition of the four velocities or four vectors. And you've seen that it's quite straightforward to have them, because once we have our four position, we know now just the name for four world lines for the trajectory of our particles. We have seen that they are constrained in a four-dimensional space, the space-time diagrams. Okay, the world lines of particles cannot be any. Photons must stick to the diagonal, whereas the massive particle must move, well, as well as photon, must move in this direction only, so forward in time. We don't have anything that goes back in time. And the inclination of the world line, wherever the particle is, cannot exceed the diagonal, because each particle is carrying its own light cone. Okay? And in that location, the velocity of our particle cannot exceed the one of light. Therefore, P is binded between the diagonals. Okay? This one if it's moving along the x direction, and this one if it's moving along the minus x direction. Then we gave a look, we defined the, where is it here? We defined the four velocity as the time derivative of x mu, the four position, with respect to the proper time. We expressed the proper time with gamma, such that we have the time of the observers not sitting together with the particle, but in another frame, so that we have this gamma factor in front. I just gave you the explicit expression for all the four components of the four velocity. And you see that in the end, we end up with this expression, or this one, depends what you want to see. And basically, the time component is strictly related to gamma, and therefore the transformation between a vector and particle and non-observer not sitting with the particle. And is not invariant. And then we gave a look at we applied basically the scalar product of Q to U. So we were just looking at the norm of this vector, and we found out that, oh, yes, it's invariant. And no matter what the particle is doing, it's always equal to minus c squared. Okay? Then we define the four velocity. It's just the derivative with respect to the proper time of the four velocity. I gave you the explicit expression by just applying here, by just plugging in here the components of the four velocity. And we end up with this expression. So the mixture of derivative of gamma dot and derivatives of the velocity, the three-dimensional velocity. Then we just gave a look at what is the change with respect to the proper time of u mu. With just these little steps, just look at them because they are just convenient for the computations of the exercises. And we end up by realizing that, yeah, I mean, this is an invariant, therefore we know that this is equal to 0, and this gives us this connection between u mu and mu, between the four velocity and the four acceleration, we realize the fact that in four-dimensional space, the four velocity is always orthogonal to the four acceleration. Then we start to look at physical property of our particle, which is the four momentum, as we would do in a standard Galilean frame, but by doing that in a four-dimensional space. Very same definition, instead of using the three-dimensional velocity, we're using the four-dimensional velocity. And by just using the definition of the four velocity, we find this expression. We realize the fact that the spatial component of the four velocity is directly related to the three-dimensional momentum of particles as we know it from school, with this gamma factor in front. And we realize the fact that if the velocity of the particle, you're dealing with non-relativistic objects, this gamma becomes 1, and we get the very same result that we have with our standard daily life, okay, for the momentum of massive objects. Then we investigated a little bit more our zeroth component of the four momentum by Taylor expanding at first order the gamma factor. And by grouping the terms properly, we realize the fact that we can identify the kinetic energy and another term, m0 c squared. And with that, we realize that this is an energy, then this must be an energy because they are the same units. Therefore, this is an energy. Particles, even if they're sitting there without doing anything, they carry an energy associated to their mass. Having that, we can now say, okay, then mc0 squared is the energy at rest for our particle. Okay? And for the zero term is E0, see, like 0 here, right, because the gamma was in front there. Therefore, I can rewrite our four momentum in this way, and you see that the energy, and you see that we don't have anymore a momentum, but we have an energy momentum, in which the zero component refers to the energy of our particle at rest with this gamma factor, and it's not at rest. Okay? Plus the gamma and V associated to the three-dimensional components of the momentum. Okay? And this tells you that from now on, you don't speak anymore about energy conservation and momentum conservation, but the object that is conserved is actually the energy momentum. Not in terms of the components, because if you are making coordinate transformations, these components are going to change. What is not going to change is the norm of the vector, is the absolute value of the vector, is going to be always the same. The transformation is such that the components shift one from another, so the numbers are changing in such a way that the norm is always the same. If you look at the norm of PP, so the norm of P, so you apply the scalar product of P to P, you get this value which is independent of your frame. Now that we can write this scalar product in these two ways, just by summing up the components, keep in mind that there is the metric, therefore we get a minus here. And by just using the definition that we gave up here of the form momentum, we have these two expressions that they are expressing the same thing. Therefore, I can put the two together, one equal to the other, and I have my full expression that gives you the energy of a particle with the energy component at rest and the one associated to the kinetic energy of the particle. Okay, so you see, here I gave you two definitions. The position, the trajectory of the particle, meaning the word line, for velocity, for acceleration, and for momentum. For momentum, that contains the information about the energy of the particle. Okay, let me give you one last definition. Let me erase one board. which is the one of the four force. Which, guess what? Again, is going to be something similar to what we did before. Then I will not call it F, but I will call it G, okay? So that I distinguish it from the three-dimensional force, as I did before with U for the four-dimensional one and V for the three-dimensional velocity, okay? Again, this is a definition, and we define this guy as the P mu over the tau. Okay, the force is not mass times acceleration. Also in Galilean frame or relativistic mechanics, the force is defined as the change with respect to time of the momentum. Okay, that's what a force is. You write F equal to ma because you are assuming that m is a constant. But if you have an object which is changing mass with time, then this is wrong. Take a rocket that you shoot on space, it's burning fuel, the gas, the material is ejected out, right? And the rocket is losing mass. Therefore, if you are considering the acceleration of a rocket, this is wrong. What you should use is force is equal to the T over the T. And now I write T because I'm just referring to the to more relativistic word. Okay? That's what a force is. Good. That's why we are going to use this definition. And what? As before, I'm just going to show you the components, G mu, which are going to be equal to gamma, the P mu over the T. Here I cut it short. I already expressed the tau as the T over gamma. And understand that I just do the derivative. Now I'm not going to do it explicitly. I just tell you that we have the standard three-dimensional force, meaning the P over the T as we see it here. So that this guy, okay, our force, that's exactly that guy, the guy there is equal to the V over C, and then we have but again, if I'm using again the definition of P, I can as well write it as gamma. So before doing the derivative, let me do it very explicitly because then it's easier to understand the rest. Okay, so I went backward. I did it because then I want to show you the connection of the first term to something that is known. What's that? This is the standard force that we know from school. No, it's more because it's containing also the energy of the particle. It's containing what? The E over the T. What's that? This is work. So it contains the work. It's expressing the work. Okay? So you have the standard time derivative. You see we have the T. We have the P over the T, which is the standard force. Okay, the three-dimensional force, which is the 1, 2, this is 1, and this is 2. Okay? Of course, there is the gamma in front. Yeah? Yeah, sorry, that's the change of energy with respect to time. Which is related to work, to the work associated to the particle. because the change of the work gives you a change in energy. Okay. Good. We are done for today. You see that I've stolen to you the minutes that I gave you last time, so everything is equal now. And as last definition, I just gave you the four force. Four force. Where is it? I lost it. Here. Okay. Okay. I gave you the four force, which is again a definition analogous to what we have in the standard Galilean non-relativistic world, and that contains two ingredients. One is related to the change of energy of our particle, and one which is related to the change of the momentum of our particle with respect to time. Therefore, one is associated to the work, to the change of energy, that is consequence of the change of energy with respect to time of our particle, which is the cause of the change of energy of our particle, and the standard force in three-dimensional as we understand it, by keeping in mind that there is this gamma in front of it. Okay, so there is a gamma times force. And again, you see that when you are dealing with non-relativistic particles, this gamma goes to 1, therefore we have the standard the P over the T equal to the force. Okay? Good. So, next lecture, we will continue with a variational approach. So we are going to investigate even more thoroughly the behaviors of massive particles. And you will see what is the machinery that then you use, we are going to use to build up electrodynamics, a few steps, to then study the Lorentz force, which is going to be a fourth force. Okay? So you see that all of those concepts are going to be used then in the next lecture. Good. Thank you very much, and I'll see you next week.